Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe you've been thinking about distant worlds, or perhaps you're simply ready to let the day slip away. Either way, you're exactly where you need to be. Tonight, we're leaving home. Not Earth exactly, but our cosmic neighborhood. We're traveling in our minds to planets orbiting other stars, worlds so distant their light takes years, decades, even centuries to reach us. Some of these planets are nothing like Earth. Others are strangely familiar, and all of them are real, waiting out there in the dark, spinning silently around suns we'll never visit. There's no rush tonight, no test at the end. Just a gentle drift through the cosmos, one discovery at a time. Let yourself get comfortable. Let your breathing slow. And if these distant worlds help carry you towards sleep, then they've done exactly what they're meant to do. If you'd like to support more journeys like this, consider subscribing. It helps other wanderers find their way here too. But for now, let's begin. The universe is vast, and tonight it's filled with planets. We've discovered thousands of worlds orbiting other stars. For most of human history, we could only wonder. Are there planets around other stars? Do worlds exist beyond the ones we can see with our own eyes? The answer remained hidden, locked in the vastness of space, until very recently. In 1992, astronomers confirmed the first planets orbiting a star other than our Sun. They weren't orbiting a normal star, but a pulsar, the spinning remnant of a dead star. Strange, hostile, and utterly unexpected, but they were there. 3 years later, in 1995, the first planet around a Sun-like star was found. It was a gas giant, massive and close to its star, nothing like anything in our solar system. And from that moment, the floodgates opened. Today, we know of more than 5,000 confirmed exoplanets, with thousands more waiting to be verified. Each one is a world with its own story, its own skies, its own silent orbit through space. We are no longer alone in knowing. The universe, it turns out, is filled with planets. Some planets orbit two suns. Imagine standing on a desert plain as two suns set together, one orange, one pale yellow, casting double shadows that stretch and merge across the sand. This isn't just science fiction, it's real. These planets are called circumbinary planets, and they orbit binary star systems, or where two stars dance around each other in a gravitational waltz. The planet traces a wide path around both, bathed in the light of two separate stars. One of the most famous is Kepler 16b, discovered in 2011. It's a cold gas giant, larger than Saturn, and it completes one orbit around its twin suns every 229 days. The stars themselves eclipse each other regularly, creating a shifting pattern of light and shadow that plays across the planet's clouds. On such a world, sunrise doesn't happen once. It happens twice, in sequence or together, depending on where you stand and when. The sky would never quite repeat itself. Every day would be subtly different, lit by a pair of flames instead of one. There are planets made almost entirely of water. We often imagine planets as rocky or gaseous, but the universe offers stranger possibilities. Some worlds are thought to be covered, not just in oceans, but in water so deep it makes up the majority of the planet's mass. These are called ocean worlds or water worlds, and beneath their surfaces, the pressure is immense. At a certain depth, water stops behaving like the liquid we know. It becomes strange, exotic forms of ice that stay solid even at high temperatures, crushed by the weight of the ocean above. Deeper still, there may be layers of superheated water, dense and mineral-rich, existing in states we can't easily replicate on Earth. Some scientists believe these planets could have hundreds or even thousands of kilometers of water, far more than Earth's oceans. No land, no continents, just water and sky, and perhaps far below, a small rocky core wrapped in endless blue. Life, if it exists there, would be entirely aquatic, drifting or swimming through pressures and darkness we can barely comprehend, silent, deep, and utterly alien. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. In our solar system, the planets follow a familiar pattern. Rocky worlds close to the Sun, gas giants farther out. But elsewhere, the rules are different. Hot Jupiters are gas giants that orbit incredibly close to their stars, sometimes closer than Mercury is to our Sun. They're scorched, tidally locked, and blasted with radiation. Their atmospheres boil. Metals vaporize in their skies. Clouds made of silicate or iron droplets drift through temperatures that can reach thousands of degrees. These planets weren't born where they are. They likely formed much farther out, in the cold outer reaches of their systems, then migrated inward over millions of years, pulled by gravitational interactions or friction with the protoplanetary disk. Their presence puzzled astronomers at first. Nothing in our solar system prepared us for worlds like this. But they are common, perhaps even more common than planets like Jupiter that stay put. On a hot Jupiter, a year might last only a few Earth days. The star fills the sky, blazing and close, a furnace that never dims. There is no night, only endless searing light. Some exoplanets rain molten glass sideways. On the planet HD 1899733b, about 64 light-years from Earth, the weather is extreme. This is a hot Jupiter, tidally locked to its star, meaning one side always faces the light, and the other is trapped in eternal darkness. The temperature difference between the two sides creates winds that rage at over 5,400 miles per hour, faster than the speed of sound. And in those winds, something strange and beautiful and terrifying happens. Glass forms in the atmosphere. Silicate particles condense into tiny shards, and the screaming winds carry them horizontally across the planet. It doesn't rain down. It rains sideways, cutting through the air like a storm of invisible blades. The planet glows a deep cobalt blue, not from water, but from the way its atmosphere scatters light, much like Earth's sky. But this blue hides violence. If you could stand there, you'd be blasted by heat, shredded by wind, and pelted by molten glass in a sideways deluge. Beautiful from a distance, lethal up close. There are rogue planets drifting through space without stars. Not all planets have a home. Some wander alone through the galaxy, unbound to any star, drifting in the cold and dark. These rogue planets may have formed around a star and then been ejected, flung out by gravitational chaos during the early violence of their system's formation. Or they may have formed independently, condensing from clouds of gas and dust like failed stars, too small to ignite fusion but large enough to be called worlds. They are invisible unless they pass in front of a distant star or emit faint infrared heat from their formation. Astronomers estimate there may be billions of them in the Milky Way, possibly outnumbering the stars themselves. Each one is a silent wanderer. No sunrise, no seasons, just the faint glow of distant galaxies and the deep cold of interstellar space. Some may have moons. Some may even have atmospheres or frozen surfaces that once knew warmth. But now they drift, solitary and forgotten, through the spaces between. One planet's year lasts just 8 hours. Imagine a world spinning so close to its star that an entire orbit, one full year, is completed in less than a single human workday. This is the reality for planets like K2, 137b, a rocky world discovered in 2017. It orbits a red dwarf star at such close range that its year lasts only about 8 hours. This planet is tidally locked, with one side eternally facing its star, baked in heat, while the other side remains in perpetual cold. The surface is likely molten, a sea of lava kept fluid by the intense radiation from its star. There are no days or nights in the way we understand them, just a frozen moment stretched across the planet's geography. One hemisphere burns, the other freezes, and between them, in the narrow twilight zone where light and dark meet, conditions might be different, cooler perhaps, still harsh but less extreme. Life as we know it couldn't survive here, but the planet itself endures, whipping around its star in a dizzying dance, year after year, in the span of hours. Some planets are darker than coal. Most planets reflect at least some of the light that hits them, but not all. TRES-2b, located about 750 light-years away, is one of the darkest planets ever discovered. It reflects less than 1% of the light that reaches it, making it darker than coal or black acrylic paint. This is a hot Jupiter, orbiting very close to its star, and yet somehow it swallows light. Scientists believe the darkness comes from its atmosphere, which contains light-absorbing chemicals like vaporized sodium and potassium, along with titanium oxide. These compounds trap light and convert it into heat. Despite being so dark, the planet glows faintly with a deep red hue, not from reflected light, but from its own heat. It's like a burning ember floating in space, visible only by the fire it holds within. In the vast catalogue of worlds, TRES-2b is a shadow, a planet that hides even as it burns. There are super-Earths larger than our planet but smaller than Neptune. Between the size of Earth and Neptune, there's a gap in our solar system. We have nothing in that range. But elsewhere in the galaxy, planets of this size are incredibly common. They're called super-Earths, and they can be anywhere from 1.5 to 10 times the mass of our planet. Some are rocky, with thick atmospheres. Others may be water worlds or have gaseous envelopes. We don't have a perfect analogy in our own system, which makes them both fascinating and mysterious. One example is LHS 1140b, a rocky super-Earth orbiting a red dwarf star about 40 light-years away. It's in the habitable zone, the region where liquid water could exist on its surface. Its gravity is much stronger than Earth's, and its skies might be thick and hazy, warmed by a cooler, dimmer star. We don't yet know what these planets truly look like up close, but they represent a type of world that may be one of the most common in the universe, and one we've never walked upon. Some planets orbit the dead remains of stars. When a star dies, it doesn't always take its planets with it. In some cases, worlds can survive the death throes of their sun and continue orbiting the remnant left behind. Pulsars are rapidly spinning neutron stars, the collapsed cores of massive stars that exploded in supernovae. They emit beams of radiation that sweep across space like cosmic lighthouses. And around some of these pulsars, planets have been found. The first exoplanets ever discovered, in 1992, orbit a pulsar called PSR, B1.57 Planck. These worlds are bathed in intense radiation, far more than any planet in our solar system. They likely formed from the debris of the supernova itself, or survived the explosion by sheer chance. Life as we know it could never exist there. But the planets remain, circling a star that is no longer a star, just a dense, spinning remnant. Silent, barren, and soaked in radiation, they drift through a graveyard of stellar death. There's a planet where it rains iron winds howl, clouds gather, and from the sky, iron falls. This is WASP 76b, a planet located about 640 light-years from Earth. It's a hot Jupiter, tidally locked to its star, with a dayside hot enough to vaporize metals. Iron evaporates into the atmosphere, carried by violent winds to the cooler night side of the planet. There, as temperatures drop, the iron condenses into droplets and falls like rain. This isn't metaphor or speculation. Observations have detected the signature of iron in the planet's atmosphere, moving from the day side to the night side, where it vanishes, likely precipitating out as liquid metal. Imagine standing in the twilight zone, where day meets night, and watching a storm of molten iron pour from the sky. Glowing orange streaks against a dark, roiling atmosphere. It would be a sight both terrifying and sublime, but no one will ever witness it in person. We can only see it from afar through the language of light and data. A storm on a distant world. Raining metal in the dark. Mini-Neptunes are the most common type of exoplanet we've found. When we look out at the galaxy and catalogue the planets we find, one type appears more than any other. Mini-Neptunes. These are planets larger than Earth but smaller than Neptune, with thick atmospheres made mostly of hydrogen and helium. They don't exist in our solar system, but they seem to be everywhere else. They occupy a size range that our models didn't predict would be so common, and their abundance has reshaped how we think about planetary formation. Some mini-Neptunes may have rocky cores wrapped in deep, dense atmospheres. Others might be more like water worlds with a gaseous envelope. We're still learning what they're made of and whether any could support life. Their atmospheres are often thick and opaque, making it hard to study their surfaces, if they even have surfaces at all. But one thing is clear. If you were to visit a random planet in the galaxy, chances are it would look something like this, larger than home, shrouded in gas, and unlike anything we've ever known. Some planets have atmospheres being blown away by their stars. Stars are not always gentle. Young stars in particular are restless and violent, emitting powerful stellar winds and bursts of radiation. For planets that orbit too close, this can be catastrophic. Their atmospheres are stripped away, molecule by molecule, blown into space like smoke in a gale. Astronomers have observed this happening in real time, watching planets lose their gaseous envelopes and shrink. One such planet is GJ 3470b, a Neptune-sized world orbiting a red dwarf star. It's losing its atmosphere at a rate of about 10,000 tons per second, fast enough that over millions of years, it may be reduced to a bare rocky core. The process is called atmospheric escape, and it's driven by heat and high-energy radiation. The planet swells slightly under the heat. Its outer layers become less tightly bound, and the star's wind peels them away. What remains may be a much smaller, denser world, stripped of its sky. Lava planets have surfaces that glow red hot. Some planets orbit so close to their stars that their surfaces never cool. They are molten, glowing worlds where rock flows like water and the ground itself radiates light. These are lava planets, and their surfaces are oceans of magma, constantly renewed by the intense heat. Temperatures can reach thousands of degrees, hot enough to melt iron, silicon, and stone. One example is 55 Cancri e, a super-Earth that orbits its star in less than 18 hours. Its surface is thought to be covered in molten rock, and it may even have an atmosphere rich in vaporized minerals. From space, it would appear as a glowing ember, faintly red or orange, pulsing with heat. There are no continents, no oceans of water, just a shifting, molten landscape beneath a hazy, toxic sky. It's a vision of primordial violence, a planet caught in a state of perpetual fire, never allowed to cool, never allowed to rest. There are planets in the habitable zone of their stars. Among all the strange, scorching, frozen and violent worlds we found, some exist in a quieter, more hopeful place. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Of course, being in the habitable zone doesn't guarantee a planet is habitable. It needs the right atmosphere, the right pressure, and countless other factors. But several planets have been found there. Proxima Centauri b, orbiting the closest star to our Sun, sits within its star's habitable zone. So does TRAPPIST-1e, part of a system with 7 Earth-sized planets. We don't yet know if any of these worlds have water, air, or life, but they represent possibilities, places where, in theory, rain could fall, rivers could flow, and under the right conditions, something might grow. In the vast darkness, these planets are small lights of potential, worlds where the universe might have tried again. One planet is so puffy it has the density of styrofoam. WASP-107b is an oddity among planets. It's about the size of Jupiter, but it weighs far, far less. In fact, its density is so low that it's been compared to cotton candy or styrofoam. If such a planet could somehow float in a cosmic ocean, it would bob at the surface like a balloon. How does a planet become so light? It's thought that WASP-107b has a very small, rocky core surrounded by an enormous, diffuse atmosphere. The star it orbits is cooler than the Sun, and the planet is far enough away that it doesn't get roasted, but is still warm enough that its atmosphere is puffed up, bloated by heat. This makes it an excellent target for studying exoplanet atmospheres, because there's so much atmosphere to observe. Telescopes can see through it more easily, detecting the chemicals and compounds swirling in its clouds. It's fragile, delicate, almost absurdly light. A giant world with almost no weight, drifting gently around its star. Some planets are older than Earth by billions of years. Earth is about 4.5 billion years old, formed in the early days of our solar system. But the universe itself is nearly 14 billion years old, and planets have been forming for most of that time. Some of the worlds we've discovered are ancient, far older than our own. One of the oldest known exoplanets is PSR B162026b, estimated to be about 12.7 billion years old. It orbits a pulsar in a globular cluster, a dense group of ancient stars. This planet formed when the universe was still very young, just over 1 billion years after the Big Bang. It has witnessed the birth and death of countless stars. It was already ancient when Earth was just a cloud of dust. If life ever existed there, it would have had billions of extra years to evolve, to think, to wonder. We'll never know. But the existence of such old worlds reminds us that the cosmos has been making planets for a very, very long time. and we are still learning to read their stories. Planets have been found orbiting 3 stars at once. Binary star systems are common. Planets orbiting 2 stars are less common but known. But what about 3? In 2016, astronomers discovered a planet in a system with not 2, but 3 stars. The planet, HD 131399AB, is a gas giant located about 340 light-years away. It orbits 1 star, while that star is in a binary pair with another, and the whole system dances with a 3rd star at a distance. From the planet's surface, assuming you could stand on its thick clouds, you would see 3 suns in the sky. Depending on where the planet is in its long, complex orbit, you might see them all rise at once, or in sequence, or arranged in shifting patterns throughout the year. The orbital dynamics are incredibly complex and chaotic. In fact, some scientists wonder whether this planet's orbit is even stable over the long term. It may eventually be flung out of the system entirely. For now, though, it remains bathed in the light of 3 suns, a world with triple shadows and skies that never quite repeat. There are frozen worlds far from their stars, while some planets roast under their suns, others shiver in the outer darkness. These frozen worlds orbit far from their stars, receiving little warmth or light. They may be covered in ice with surfaces of frozen water, methane, or ammonia. Beneath the ice, though, some might hide liquid oceans, kept warm by tidal heating or radioactive decay in their cores. In our own solar system, moons like Europa and Enceladus show us what's possible. But exoplanets can be much larger, and their hidden oceans could be vast. These worlds exist in the cold, quiet reaches of their systems, where starlight is faint and the sky is full of stars. They don't get much attention compared to hot Jupiters or habitable zone planets, but they may be more common. And beneath their frozen shells, in the dark and silence, there may be seas, warm, still, waiting. Some planets could have rings more spectacular than Saturn's. Saturn's rings are one of the most beautiful sights in our solar system, but they may not be unique. Some exoplanets likely have rings too, and some of those rings could be even grander. One candidate is J1407b, sometimes called Super Saturn, a planet or brown dwarf located about 434 light-years away. Observations suggest it has a ring system so large and dense that it would make Saturn's look modest by comparison. The rings may span a distance wider than the orbit of Earth around the Sun, with gaps carved out by unseen moons. If such a planet were in our solar system in place of Saturn, its rings would be visible to the naked eye from Earth, stretching across the night sky like a glowing arc. We've never directly seen the rings of an exoplanet, but we've detected their shadows, their dips in light as they pass in front of their stars. Somewhere out there, a world is wrapped in halos of ice and rock, turning slowly, beautifully, beneath a distant sun. Planets can have multiple moons or none at all. Earth has 1 moon. Mars has 2 tiny ones. Jupiter and Saturn have dozens. But what about planets beyond our solar system? We haven't yet directly detected any exomoons, but it's almost certain they exist. Large gas giants, in particular, could host families of moons, some perhaps large enough to have their own atmospheres or even oceans. The challenge is detecting them. Moons are small, and their signals are faint. But in 2018, astronomers found evidence of a moon orbiting the planet Kepler 1625b, a gas giant in the habitable zone of its star. If confirmed, this exomoon would be about the size of Neptune, far larger than any moon in our solar system. Other planets may have no moons at all, especially those that orbit close to their stars, where tidal forces would tear moons apart or pull them away. The presence or absence of moons can shape a planet's climate, its tides, its rotation. They are not just decoration, they are part of the story. Diamond planets might exist in carbon-rich systems. In systems where carbon is more abundant than oxygen, chemistry takes a different path. Instead of silicate rocks, you might get carbides. Instead of water ice, you might get diamonds. Some exoplanets, particularly those orbiting pulsars or forming in carbon-rich environments, could have layers of crystalline carbon deep within their mantles, or even on their surfaces. These are sometimes called diamond planets, though they wouldn't sparkle like a jewel. They'd be dark, dense, and incredibly hard. One candidate is 55 Cancri E, the lava planet mentioned earlier. Some models suggest that beneath its molten surface, there could be vast amounts of diamond formed under extreme pressure and heat. We'll never mine it, we'll never see it, but the idea itself is dazzling. A world where the ground is made of what we consider precious, a planet whose value, by Earth standards, would be incalculable. Yet there it spins alone and untouched, in the indifferent dark. Some planets may have violent volcanic activity. Volcanoes shape worlds. On Earth, they've built mountains, created islands, and released gases that formed our atmosphere. On Io, Jupiter's moon, volcanic eruptions are constant and dramatic, and on some exoplanets, volcanic activity could be even more extreme. Planets that are tidally heated, stretched, and squeezed by their stars or neighboring planets can have interiors that stay molten and restless. One such world might be Corot 7b, a rocky planet about 1.7 times the size of Earth. It orbits so close to its star that its surface is likely molten, and models suggest it could have massive volcanic eruptions, spewing lava and gas into space. The planet's gravity might not be enough to hold onto all of its atmosphere, so the eruptions could constantly replenish what's lost. It would be a world in flux, constantly resurfacing, constantly releasing, a furnace that never cools. Life couldn't survive there, but the planet itself is alive with fire. There are Neptune-like ice giants with thick atmospheres. In our solar system, Neptune and Uranus are ice giants, large planets with thick atmospheres made mostly of hydrogen and helium, surrounding mantles of water, methane, and ammonia ices. Beyond our system, similar planets have been found, though often much closer to their stars. These are sometimes called hot Neptunes, and they can have atmospheres that are much more active and easier to study than their distant cousins. One example is HAT P11b, located about 123 light-years away. It's slightly larger than Neptune and orbits its star in just under 5 days. Its atmosphere contains water vapor, and it's one of the smallest exoplanets for which we've been able to study atmospheric composition in detail. These worlds are common, but they're hard to understand. Are they failed gas giants, scaled-up super-Earths? The truth is, we're still learning, but each one teaches us something new about how planets form, evolve, and endure. Planets can migrate over time, changing their orbits dramatically. When planets first form, they don't always stay put. The early solar system was chaotic, with planets tugging on each other, colliding, and sometimes shifting their orbits. The same is true elsewhere. Planetary migration is the process by which planets move inward or outward over time, driven by interactions with the protoplanetary disk, with other planets, or with their star. Hot Jupiters, for example, didn't form close to their stars. They started farther out and spiraled inward, either through friction with the gas disk or through gravitational scattering. Some planets may have even swapped places with their siblings, leapfrogging past each other in a cosmic game of musical chairs. This migration can be gentle or violent, slow or fast. It can eject planets entirely, sending them into interstellar space. It can also bring planets into the habitable zone, or pull them out of it. The solar system we see today is not the one that was born. It's the one that survived. Some planets are so hot their atmospheres are ionized. On the most extreme worlds, heat does more than melt rock or vaporize water. It tears molecules apart. At temperatures exceeding several thousand degrees, atoms lose their electrons, and the atmosphere becomes a plasma, a glowing, electrified soup of charged particles. These ultra-hot Jupiters are some of the most extreme environments we've found. One example is Kelt 9b, the hottest known exoplanet, with dayside temperatures reaching over 7,800 degrees Fahrenheit, hotter than many stars. At these temperatures, molecules like water and methane can't survive. Instead, the atmosphere is filled with atomic hydrogen, ionized metals, and glowing clouds. The planet is so hot it's thought to be slowly evaporating, losing mass to space. It won't last forever. Over time, it may shrink, its atmosphere stripped away by heat and radiation, until only a dense core remains. But for now, it glows, a blazing world on the edge of destruction, radiating heat into the void. There are planets with extreme day-night temperature differences on Earth. The difference between day and night temperatures can be noticeable, but is usually mild. On some exoplanets, the difference is staggering. Tidally locked planets, where one side always faces the star and the other is in perpetual darkness, can have temperature swings of thousands of degrees from one hemisphere to the other. The day side might be hot enough to melt lead, while the night side is cold enough to freeze gases solid. These temperature extremes drive fierce winds, as heat from the day side tries to flow to the night side, creating storms and atmospheric circulation patterns unlike anything on Earth. In some cases, the night side may be cold enough for clouds to form and rain to fall, while the day side stays clear and scorching. The twilight zone, the narrow band between day and night, becomes the most interesting region, where temperatures are more moderate and conditions less extreme. It's a place of eternal sunset or eternal sunrise, depending on which way you're facing. Brown dwarfs blur the line between planet and star. Not everything in space fits neatly into categories. Brown dwarfs are objects that are too large to be planets, but too small to be stars. They form like stars from the collapse of gas clouds, but they never accumulate enough mass to sustain hydrogen fusion in their cores. Instead, they glow faintly from leftover heat and, in some cases, from the fusion of deuterium, a heavier form of hydrogen. They're sometimes called failed stars. Some of the largest exoplanets we've discovered are close in mass to the smallest brown dwarfs, making the boundary between planet and brown dwarf unclear. Where do you draw the line? Is it about how they form or how massive they are or what they're made of? astronomers are still debating. But in that grey area between world and almost star, there are objects that challenge our definitions. Dim, warm, and solitary, they drift through space, not quite one thing or the other. Some planets orbit in the opposite direction of their star's rotation. In our solar system, all the planets orbit the Sun in the same direction the Sun rotates. This is because they all form from the same spinning disk of gas and dust. But some exoplanets orbit in the opposite direction, a configuration called retrograde. How does this happen? It's usually the result of gravitational interactions, close encounters with other planets or passing stars that flip the orbit. One such planet is HAT P7b, a hot Jupiter with a retrograde orbit. From the planet's perspective, its star would appear to rise in the west and set in the east, opposite to what we see on Earth. These backward orbits tell a story of chaos and violence in the planet's past, a reminder that not all systems are as orderly as ours. Some have been shaken, stirred, and rearranged by forces we're only beginning to understand. Planets can lose their atmospheres and regain them. Atmospheres are not permanent. They can be stripped away by stellar wind, impacts, or volcanic activity. But in some cases, they can also be replenished. A planet with active volcanoes can release gases back into the air, rebuilding what was lost. A planet with a lot of water or ice can generate steam through heating or impacts, creating a new atmosphere from within. Venus, in our own solar system, may have lost and regained its atmosphere multiple times over its history. The same could be true for exoplanets, especially those in dynamic, violent systems. An atmosphere is not a fixed feature. It's part of an ongoing process, a balance between loss and renewal, destruction and creation. Some planets breathe in and out over geological time, shrouded in gas, then stripped bare, then shrouded again. The sky above is not eternal. It's temporary, fragile, and constantly rewritten. There are worlds with skies that glow in strange colors. On Earth, the sky is blue during the day and fades to orange and red at sunset. But on other planets, the sky could be green, purple, orange, or even brown, depending on the composition of the atmosphere and the color of the star. Planets orbiting red dwarf stars, for example, might have skies that are dimmer and redder. Planets with thick hazes of methane or other hydrocarbons could have orange or brown skies, like Titan, Saturn's largest moon. Some planets might have no sky color at all, just blackness, if their atmospheres are too thin. Others might shimmer with strange optical effects caused by ice crystals, dust, or layers of different gases. The sky is not universal. It's a reflection of chemistry, light, and perspective. And on distant worlds under different suns, it could be something we've never imagined. A ceiling of color and cloud shaped by alien physics, glowing softly in the light of a star we'll never see up close. Planets can have clouds made of rubies and sapphires. When we think of clouds, we picture water vapor, perhaps wisps of ice crystals drifting across a blue sky. But chemistry elsewhere can be very different. On some hot exoplanets, temperatures and pressures create clouds made of corundum, the mineral that forms rubies and sapphires. These gemstone clouds drift through skies where the heat turns solid minerals into vapor, which then condenses high in the atmosphere. HAT P7b is one such world. Models suggest that aluminum oxide, the compound that makes up corundum, could condense into tiny crystals that scatter and reflect light. The result might be clouds that shimmer red or blue, depending on trace elements and how the light hits them. Of course, you'd never see them sparkle the way a cut gem does. They'd be microscopic particles suspended in a haze, but chemically, they're the same. A sky filled with floating rubies, invisible to the eye, known only through the signatures they leave in starlight. Some planets may have supersonic winds. Wind on Earth can be powerful. Hurricanes reach speeds of over 150 miles per hour, enough to level buildings and reshape coastlines. But on some exoplanets, winds blow far faster, breaking the sound barrier, and then some. HD 189733b, the planet where it rains glass, has winds clocked at over 5,400 miles per hour, more than 7 times the speed of sound. These aren't gentle breezes. They're roaring streams of atmosphere, driven by extreme temperature differences between day and night. The heat on the day side causes the atmosphere to expand and rise, creating pressure differences that force air toward the cooler night side. The planet's rotation adds a twist, creating jet streams that race around the equator at blistering speeds. If you could somehow float in that atmosphere, you'd be swept along faster than a bullet, carried by winds so powerful they'd tear anything apart. It's a world in constant motion, never still, never calm, always screaming. There are planets where the surface pressure could crush. A submarine pressure is a force we rarely think about. On Earth's surface, atmospheric pressure is about 14.7 pounds per square inch, comfortable for life as we know it. But go deep underwater, and pressure increases rapidly. At the bottom of the Mariana Trench, it's over 1,000 times surface pressure. On some super-Earths and mini-Neptunes, surface pressures could be even more extreme. Hundreds or thousands of times what we experience, enough to crush the hull of a submarine like a soda can. These planets might have thick, heavy atmospheres composed of hydrogen, helium, or other gases, pressing down with immense weight. Below that, if there's a surface at all, it might be an ocean or a layer of exotic ices compressed into strange forms. We don't fully understand what conditions are like on such worlds, but they're hostile to anything we could build or send. The pressure alone would be lethal. A weight so great it changes the behavior of matter itself. In these depths, even the concept of surface becomes unclear. Planets orbiting red dwarf stars might be the most common. Red dwarfs are the most abundant type of star in the galaxy, small, cool, and incredibly long-lived. They burn their fuel so slowly that they can last for trillions of years, far longer than the current age of the universe. And around many of these dim red stars, planets have been found. In fact, it's estimated that nearly every red dwarf has at least one planet, and many have several. This means that the most common type of planetary system in the Milky Way is likely very different from our own. Planets in the habitable zones of red dwarfs orbit much closer to their stars than Earth does to the Sun. Because red dwarfs are so faint, this close proximity means they're often tidally locked, with one side always facing the star. They're also exposed to frequent stellar flares, bursts of radiation that could strip atmospheres or sterilize surfaces. But they're there, billions and billions of them, quietly circling their small red suns. If life exists elsewhere, it may have arisen not under a yellow star like ours, but under the dim, ruddy glow of a red dwarf. Some planets might have auroras far more intense than Earth's on Earth. The aurora borealis and australis are gentle, shimmering curtains of light, caused by charged particles from the Sun interacting with our magnetic field. They're beautiful, but relatively mild. On some exoplanets, especially those with strong magnetic fields and close proximity to active stars, auroras could be far more dramatic. They might cover entire hemispheres, glow bright enough to see in daylight, or flicker constantly with violent intensity. Hot Jupiters, which orbit close to their stars and are bathed in stellar wind, could have permanent auroras wrapping around their poles, or even their equators. Some of these planets might glow faintly in the dark, lit not by their star, but by their own magnetic storms. We've detected radio emissions from some exoplanets that suggest powerful auroral activity, signals that hint at invisible light shows playing out across alien skies. On such worlds, the night would never be fully dark. The sky would dance, always with electric fire. Lava lakes could exist on the surfaces of hot rocky planets. On Io, Jupiter's moon, lava lakes bubble and churn, fed by intense volcanic activity driven by tidal forces. On some rocky exoplanets that orbit very close to their stars, similar lakes could exist. But on a much larger scale, the constant heat from the star could keep portions of the surface molten, forming vast pools of liquid rock that glow with their own light. These lakes might be temporary, crusting over and then reopening as the planet's rotation carries them into cooler regions. Or they might be permanent, especially on tidally locked worlds where the day side never cools. Imagine a landscape of flowing magma, incandescent orange and red, bordered by blackened cracked plains. The air above would shimmer with heat. Gases would rise, condense and rain back down, creating a cycle of evaporation and precipitation, not of water, but of rock. It's a vision of a planet in its infancy, or perhaps locked in eternal infancy, never allowed to cool, never allowed to solidify, molten, glowing, and restless. There are planets that formed in one star system and were captured by another. Not all planets stay with the star they were born around. In dense star clusters or during close encounters between stars, planets can be stolen. A passing star's gravity can pluck a planet from its original orbit and carry it away. Or a planet can be ejected from one system and later captured by another. This process is called planet capture, and while it's rare, it's possible. Some of the planets we've found in unusual orbits, especially those around binary stars or in unstable configurations, might be captured worlds. They didn't form where they are now. They're immigrants, cosmic wanderers that found a new home by chance. Their skies would show a different sun than the one that warmed them in their youth. Their geology, their chemistry, even their moons, if they have any, would carry the signature of a different origin. They are strangers in a strange system, adopted by gravity and time. Some planets might have multiple layers of clouds at different altitudes. On Earth, clouds form mostly in the troposphere, the lowest layer of our atmosphere. But on gas giants and mini-Neptunes, atmospheres can be much thicker and more complex, with multiple cloud decks stacked at different altitudes. Each layer might be made of different materials, depending on temperature and pressure. At high altitudes, you might have wispy clouds of ammonia or methane. Lower down, water clouds. Deeper still, clouds of ammonium hydrosulfide or other exotic compounds. Jupiter and Saturn show us hints of this layered structure. But on exoplanets, the variety could be even greater. Some might have layers of silicate clouds, salt clouds, or metal clouds, each forming at a specific depth where conditions are just right. These layers can interact, mixing and separating, creating bands, storms, and swirling vortices. The atmosphere becomes a three-dimensional landscape, not just a blanket of air, but a complex shifting environment where weather happens at many levels, all at once. Planets far from their stars might be kept warm by tidal heating. You don't need a nearby star to stay warm. In some cases, a planet's own moon or its interaction with other planets can generate heat through a process called tidal heating. This happens when gravitational forces stretch and squeeze the planet, creating friction in its interior. The friction generates heat, which can keep the interior molten or even maintain subsurface oceans beneath a frozen crust. This is how Europa and Enceladus, moons of Jupiter and Saturn, stay warm enough to have liquid water beneath their icy shells. The same could be true for exoplanets, especially those in multi-planet systems where gravitational interactions are strong. A planet far from its star, cold and dark on the surface, might be warm and alive beneath. Its ice might be thin in places, cracked and shifting, with geysers of water vapor shooting into space. Life, if it exists, could thrive in the hidden depths, insulated from the cold, fed by heat from below, silent, secret, and waiting. Some exoplanets might have rings of dust from shattered moons. Rings aren't just for gas giants. Some rocky planets could have rings too, though they'd be formed differently. Instead of ice and rock left over from formation, these rings might come from moons that ventured too close and were torn apart by tidal forces, a boundary called the Roche limit. When a moon crosses this line, the planet's gravity pulls it apart, scattering debris into orbit. Over time, this debris forms a ring, thin and dusty, encircling the planet like a delicate halo. Such rings would be temporary on astronomical timescales, gradually spreading out and falling back to the planet or escaping into space. But for a while, they'd be there, visible from the surface as a faint arc across the sky, a memorial to a moon that came too close. Some planets we've observed show hints of rings or debris disks, though we've yet to confirm them directly. Somewhere, a ringed rocky world might be turning slowly, wrapped in the shattered remnants of its past. Planets can have magnetic fields far stronger than Earth's magnetic field protects us from solar wind and cosmic radiation, creating a shield that makes life on the surface possible. Some exoplanets have magnetic fields too, and some may be far more powerful than ours. Gas giants, especially those with rapid rotation and liquid metallic hydrogen in their interiors, can generate intense magnetic fields that extend far into space. These fields can interact with stellar wind, creating massive magnetospheres, regions where charged particles are trapped and accelerated. They can also produce powerful radio emissions, which we've detected from some exoplanets, even though we can't see the planets themselves. A strong magnetic field can protect a planet's atmosphere from being stripped away, but it can also create hazards. Radiation belts, like Earth's Van Allen belts but far more intense, could make the space around such planets dangerous, even deadly. The field itself is invisible, but its effects ripple outward, shaping the environment around the planet in profound ways. There are planets where a day is longer than a year. On most planets, a day, the time it takes to rotate once on its axis, is shorter than a year, the time it takes to orbit the star. but not always. Venus, in our own solar system, rotates so slowly that its day is actually longer than its year. The same is true for some exoplanets, especially those that are tidally locked or have very slow rotation rates. On such worlds, the sun moves across the sky with agonizing slowness, taking weeks, months, or even longer to complete a single sunrise to sunset cycle. If the planet orbits quickly, it might complete several orbits before the sun even sets. Time would feel distorted, stretched. Seasons, if they exist, would blend into one another. The rhythm of day and night, so fundamental to life on Earth, would be broken or inverted. It's a strange kind of world where the clock of rotation and the clock of orbit are out of sync, ticking at different rates, never quite aligning. Some planets might have been ejected from their original solar systems. Planetary systems are not always stable. During their formation or over millions of years of gravitational interactions, some planets can be flung out of their systems entirely. These ejected planets become rogues, drifting through interstellar space. They may have formed in the warm inner regions of a system, perhaps even in a habitable zone, before being cast out into the cold and dark. If such a planet had water, moons, or even life, what would happen to it after ejection? The surface would freeze, but beneath a thick layer of ice, insulated by distance and time, a subsurface ocean might persist, heated by radioactive decay or tidal forces from a large moon. Life, if it existed, might endure in that hidden sea, unaware that its world no longer orbits a star. These ejected planets carry with them the ghosts of their origins, worlds that once knew warmth, now adrift, silent and alone. Planets can form around dying stars or in the remnants of supernovae. We usually think of planets forming in the disks around young stars, but they can also form later in unexpected places. Some planets orbit white dwarfs, the dim, cooling remnants of sun-like stars. Others orbit pulsars, the rapidly spinning cores left after supernova explosions. These planets likely formed from the debris of the stellar death itself, or their survivors that somehow endured the violence. In the case of pulsars, the planets are bathed in intense radiation, pulsing with every rotation of the star. They're not habitable, but they're proof that planet formation can happen in the aftermath of destruction. From the ashes of a dead star, new worlds can be born. It's a quiet testament to the resilience of matter, to the way gravity pulls things together even after everything has been blown apart. Death and birth, always intertwined, even in the cosmos. Some planets orbit so quickly, they're stretched into egg shapes. Gravity doesn't just pull planets toward their stars. It can also stretch and deform them. Planets that orbit very close to their stars experience strong tidal forces, which pull more strongly on the side facing the star than on the far side. Over time, this stretches the planet, making it slightly elongated, like an egg. The effect is subtle on most planets, but on hot Jupiters and other close-in worlds, it can be significant. WASP-12b, one of the hottest known exoplanets, is thought to be stretched so much that it's visibly distorted. Its shape is no longer a perfect sphere, but an ellipsoid, bulging toward its star. The planet is also being slowly consumed, with material from its atmosphere spiraling inward, feeding the star. It's a world in the process of being torn apart, reshaped by gravity, its form dictated by forces beyond its control. In the end, it may not survive, pulled apart entirely, leaving only a faint trace in the stellar wind. there are planets made mostly of carbon instead of silicon. On Earth, and most rocky planets in our solar system, the crust is dominated by silicate minerals, compounds made of silicon and oxygen. But in systems where carbon is more abundant than oxygen, the chemistry is different. Instead of silicates, you get carbides. Instead of granite and basalt, you might have graphite, diamond, or silicon carbide. These are carbon planets, and they would be fundamentally different from anything we know. A carbon planet might have a surface of tar-like hydrocarbons with layers of diamond beneath. It wouldn't have plate tectonics the way Earth does, because the materials don't behave the same way under pressure. Its atmosphere might be rich in carbon monoxide or methane. Even the color will be different, darker, less reflective. We haven't confirmed any carbon planets yet, but some candidates exist, and their chemistry fascinates scientists. They represent a different branch of planetary evolution, a path not taken in our own system, but viable elsewhere. Some planets might have snowfall made of metal. Snow is usually ice, frozen water drifting gently from the sky. But on hot exoplanets, snow can be made of metal. On worlds where temperatures are high enough to vaporize metals like iron or titanium, these metals can rise into the upper atmosphere, where it's cooler. There, they condense into tiny metallic flakes, which then fall back down like snow. On WASP-76b, where it rains iron, this process happens constantly on the night side. The day side vaporizes the metal, winds carry it across the planet, and on the cooler night side, it precipitates out. You might see a glittering metallic haze, or individual flakes catching the dim light as they fall. It wouldn't look like snow on Earth, soft and white. It would be dark, heavy, and reflective, a slow drift of metal returning to the surface. Another reminder that on distant worlds, even the most familiar processes can take on alien forms. Planets in binary star systems can have complex seasons. On Earth, seasons are caused by the tilt of our axis as we orbit the Sun. But on planets in binary star systems, especially those that orbit both stars, seasons can be far more complicated. The planet receives light and heat from two sources, each following its own path across the sky. Depending on where the planet is in its orbit and where the stars are relative to each other, the amount of light and warmth can vary dramatically. There might be periods when both stars are overhead, flooding the planet with heat. Other times, one star might be eclipsed by the other, or both might be on the horizon, creating a brief, cooler twilight. Over the course of a year, which itself might be irregular, the planet could experience multiple hot and cold periods that don't follow a predictable pattern. Predicting the weather, or even knowing when to plant crops if anyone lived there, would be a challenge. Seasons would be less a cycle and more a shifting, unpredictable dance of light and shadow. Some planets have been discovered using the wobble of their stars. Most exoplanets are found using the transit method, watching for dips in a star's light as a planet passes in front of it. But there's another way, the radial velocity method. As a planet orbits, it doesn't just move around the star. It also pulls on the star, causing the star to wobble slightly. This wobble shifts the star's light toward the red or blue end of the spectrum, depending on whether it's moving away from us or toward us. By measuring these tiny shifts, astronomers can detect planets they can't see directly. The first exoplanet around a Sun-like star, 51 Pegasi b, was discovered this way in 1995. The method works best for large planets close to their stars because they cause the biggest wobbles. But with sensitive instruments, even smaller planets can be detected. It's a subtle technique, reading motion from light, inferring presence from absence. And it works. The wobble is faint, but it's there. A gravitational fingerprint left by an unseen world. There are planets so dark we can barely detect them. Some planets don't just fail to reflect much light. They're so dark and orbit stars so faint that detecting them at all is a challenge. These planets might be far from their stars, shrouded in thick clouds, or made of materials that absorb light rather than reflect it. They're like shadows in space, visible only through indirect methods. The wobble they cause in their star, the brief dimming as they pass in front of it, or the faint infrared glow of their own heat. Rogue planets too are incredibly hard to detect. Without a star to illuminate them or pass in front of, they're nearly invisible. We find them through microlensing, watching how their gravity bends the light of more distant stars. It's a rare, fleeting event. But when it happens, we catch a glimpse of something we'd never see otherwise. A world alone in the dark, silent and unseen, drifting through the galaxy, felt only by the light it bends as it passes. Planets can have moons larger than Mercury. In our solar system, some moons are quite large. Ganymede, Jupiter's largest moon, is bigger than the planet Mercury. Titan, Saturn's largest moon, has a thick atmosphere and liquid lakes on its surface. If gas giant exoplanets have similar moons, some of them could be worlds in their own right, large, geologically active, and potentially even habitable. A moon orbiting a gas giant in the habitable zone could have liquid water, a breathable atmosphere, and stable conditions, even if the planet itself is not habitable. This kind of moon, called an exomoon, could be a refuge for life in systems where the planets themselves are too harsh. We haven't yet confirmed any exomoons, but the search is ongoing. If they exist, they add another layer of possibility to the search for life. Not just planets, but the moons of planets, each one a potential home, hidden in the shadow of giants. Some planets might have been habitable in the past. Conditions on a planet aren't fixed. Stars change over time. They get brighter as they age. Or in the case of red dwarfs, they start out violent and gradually calm down. A planet that's too hot now might have been in the habitable zone billions of years ago. Or a planet that's frozen now might once have had liquid water when its star was younger and cooler. Mars is a perfect example in our own system. It was once warmer and wetter, with rivers and perhaps even oceans. Now it's cold and dry, its atmosphere stripped away. The same story could be playing out on countless exoplanets. Life might have arisen, flourished, and then vanished as conditions changed. Or it might have adapted, moving underground, into caves, or beneath ice. When we look at a planet, we're seeing a single moment in its history. We don't know what it was, or what it will become, only what it is now. Planets can reflect almost no light, or shine brightly. Albedo is the measure of how much light a planet reflects. Earth's albedo is about 0.3, meaning it reflects 30% of the sunlight that hits it. But planets can vary widely. TRES-2b, as mentioned, reflects less than 1%, darker than charcoal. On the other end, some planets with thick, bright clouds can have albedos close to 1, reflecting almost all the light they receive. These bright planets might be covered in clouds of sulfuric acid, like Venus, or ammonia, like parts of Jupiter. They'd appear as brilliant points of light, shining almost like small stars themselves. Albedo affects a planet's temperature and visibility. A dark planet absorbs more energy and heats up. A bright planet stays cooler, reflecting heat back into space. It also affects how easily we can see them. Bright planets are easier to detect by direct imaging. Dark planets hide, visible only through their shadows or the wobbles they create. Some planets orbit in highly elliptical, stretched-out paths. Most planets have nearly circular orbits, but not all. Some follow elongated ellipses, swinging close to their stars at one point in their orbit, and then looping far away. These eccentric orbits create extreme seasonal variations. When the planet is close, it receives intense heat and radiation. When it's far, it cools dramatically. The difference can be stark, and it affects everything: atmosphere, weather, and the possibility of life. HD 2782 b has one of the most eccentric orbits known, swinging from a distance where it's relatively cool all the way in to a scorching close approach. Each orbit is a journey from winter to summer and back again, compressed into a single year. For any life trying to survive there, the challenge would be immense. Adaptation would have to be rapid and flexible. But even without life, these planets are dynamic, constantly changing, never in equilibrium. They're restless worlds, shaped by the sweep of their paths through space. There are planets where temperatures allow exotic states of matter. On Earth, we're familiar with solids, liquids, and gases. But under extreme conditions, matter can exist in stranger forms. On some exoplanets, especially super-Earths with thick atmospheres and high pressures, water might exist as supraeonic ice, a state where oxygen atoms form a solid lattice while hydrogen ions flow freely through it like a liquid. It's both solid and conductive, a hybrid state that doesn't exist naturally on Earth. On gas giants with extreme pressure and temperature, hydrogen itself can become metallic, conducting electricity and generating powerful magnetic fields. Deeper still, in the cores of massive planets, matter might exist in states we can only model with computers, too extreme to replicate in any lab. These exotic states shape the planet's structure, its magnetism, its heat flow. They're invisible from outside, but essential to understanding how these worlds work. Matter, it turns out, has more forms than we see in our daily lives, and on distant planets, it explores them all. Some planets have been imaged directly by telescopes. Most exoplanets are detected indirectly through the effects they have on their stars. But a few have been imaged directly, photographed as tiny points or smudges of light next to their much brighter stars. This is incredibly difficult. Stars outshine their planets by millions or billions of times, making it like trying to see a firefly next to a searchlight. But with special instruments that block out the star's light, astronomers have managed to capture images of a handful of planets. These are usually young, hot gas giants orbiting far from their stars, still glowing with the heat of their formation. Each image is precious, a rare glimpse of a world not through inference, but through sight. We see them as they are, or rather, as they were when their light began its journey to us. Tiny dots of light in the darkness, proof that these distant worlds are not just numbers and data. They're real. Planets may have underground oceans of liquid methane or ammonia water. Isn't the only liquid that can exist beneath the planet's surface. On worlds that are colder, or with different chemistries, subsurface oceans might be made of methane, ammonia, or other compounds. Titan, Saturn's moon, has liquid methane and ethane on its surface, forming lakes and seas. Beneath the surface, it might have a water-ammonia ocean. Some exoplanets, especially those far from their stars, could have similar environments. A thick, icy crust might insulate a liquid layer beneath, kept warm by tidal heating or radioactive decay. These exotic oceans would be cold by Earth standards, but they'd still be liquid. And in the universe, liquid often means possibility. Chemistry can happen, energy can flow, structure can form. Whether life could arise in a methane ocean is an open question. But the fact that such oceans might exist at all expands the places we look and the forms we imagine life might take. Some planets might have glowing auroras visible from space. Auroras on Earth are beautiful, but relatively faint, visible mostly at night in polar regions. On some exoplanets, especially those with strong magnetic fields and close orbits around active stars, auroras could be so intense they glow bright enough to be seen from space, even as daylight. These auroras might not be confined to the poles, but could wrap around the planet, creating a shimmering halo of light. They'd be driven by constant bombardment from stellar wind, charged particles streaming from the star and colliding with the planet's magnetic field. The result would be a continuous light show, flickering and pulsing, visible in ultraviolet, visible light, or even radio waves. Some astronomers believe we might be able to detect these auroras before we detect the planets themselves, using their glow as a signpost. A planet lit not by its star, but by its own magnetic fury, glowing softly in the dark. Planets can have incredibly long orbital periods. While some planets orbit their stars in hours or days, others take much, much longer. In our solar system, Neptune takes about 165 Earth years to complete one orbit. Some exoplanets orbit even more slowly, taking centuries or millennia to make a single trip around their stars. These distant cold worlds are hard to detect because we have to watch them for so long to see their orbit. Some may be more like large asteroids or dwarf planets, barely planets at all. Others are full-sized gas giants, drifting in the outer darkness of their systems. For these planets, a year is longer than recorded human history. Generations could pass without a single season changing. Time moves differently out there, slow and patient, measured in centuries instead of months. And yet, they turn, quietly, steadily, tracing their wide arcs through space. There are planets we'll never be able to visit. It's a sobering thought, but true. The distances between stars are so vast that even with our fastest current spacecraft, it would take tens of thousands of years to reach the nearest star. The exoplanets we've discovered are even farther, hundreds or thousands of light years away. With current technology, visiting them is impossible. Even with future breakthroughs, sending humans to another star system remains a monumental, perhaps insurmountable challenge. We may only ever see these worlds through telescopes, studying them from afar, analyzing their light, their atmospheres, their orbits. We might detect signs of life if it exists, but we won't walk on their surfaces or breathe their air. They remain distant, unreachable, known only through the stories their light tells as it crosses the void. And perhaps that's enough, to know they're there, to understand, even from a distance, that the universe is filled with worlds, each one real, each one turning, each one part of a cosmos far larger than we'll ever touch. Planets are still forming right now, in young star systems. Planet formation isn't a relic of the past. It's happening right now, in star-forming regions throughout the galaxy. Around young stars, disks of gas and dust swirl and clump, colliding and sticking together, building up from dust grains to pebbles to boulders to planetesimals, and eventually to planets. We can see this process in action, observing protoplanetary disks with gaps and rings that mark where planets are being born. H.L. Tauri, a young star about 450 light-years away, has a disk with multiple bright rings, each one likely the orbit of a forming planet. These planets are still gathering material, still growing, still finding their final form. In a few million years, the disk will clear, and a new planetary system will be revealed. Right now, somewhere in the galaxy, a planet is being born. Matter is coming together, shaped by gravity and time, building a world that will one day orbit silently through space. Some planets might support life in forms we can't yet imagine. When we think of life, we think of what we know. Carbon-based, water-dependent, thriving in moderate temperatures. But the universe is vast, and chemistry is flexible. Life might arise in forms we haven't considered. In the clouds of gas giants, in subsurface oceans of methane, in the atmospheres of hot Jupiters, where chemistry is extreme. We don't know what's possible until we look. Some scientists propose that life could be based on silicon instead of carbon, or use ammonia instead of water. Others imagine life that exists as patterns of information in plasma, or as slow-moving colonies in frozen nitrogen. These ideas are speculative, but they push us to think beyond what we know. Life on Earth is one experiment, but the universe has run countless others. And on some distant planet, under an alien sky, life might be thriving in a form we wouldn't even recognize. Different chemistry, different structure, but still somehow alive. Studying exoplanets helps us understand our own planet better. Every exoplanet we discover teaches us something about Earth. Why do we have the atmosphere we do? Why is our orbit stable? Why do we have one large moon and not many small ones? By looking at other systems, we see what's common and what's unique. We learn how planets form, how they evolve, and how rare or common Earth-like conditions might be. Some exoplanets show us what Earth might have been like in its past, or what it could become in its future. Others show us alternate paths, worlds that started like Earth but ended up completely different. Venus is a reminder that even a planet in the habitable zone can become hellish. Mars shows us that atmospheres can be lost. Every discovery adds to our understanding, not just of other worlds, but of our own. We see ourselves more clearly by looking outward. Planets remind us that we are part of something vast. In the quiet of the night, under the stars, it's easy to feel small. And in one sense, we are. Earth is a tiny world, orbiting an average star in the outer spiral arm of a galaxy that contains hundreds of billions of stars. And each of those stars may have planets of its own. The numbers are staggering, the distances unimaginable, and yet we're part of it. Made from the same atoms, shaped by the same forces. Every planet we discover is a reminder that the universe is not empty. It's full of worlds, full of possibility, full of stories being written in gravity, light and time. We'll never visit most of them. We may never even see them directly, but knowing they're there changes something. It expands the horizon of what's real. and it places us not at the center, but as one part of a vast interconnected whole, a single note in a symphony too large to hear all at once. The search for exoplanets is still just beginning. We've found thousands of planets, but the galaxy contains hundreds of billions of stars and likely even more planets. We've barely scratched the surface. Most of the planets we've found are large, close to their stars, or both, because those are the easiest to detect. Smaller, Earth-like planets, especially those in the habitable zones of Sun-like stars, are harder to find. But technology is improving. New telescopes are being built. New methods are being refined. In the coming years and decades, we'll find more. We'll characterize their atmospheres, study their climates, and search for signs of life. We'll learn whether Earth is rare or common, whether life is an accident or an inevitability. The search is patient, methodical, and ongoing. And with every new discovery, the universe reveals itself a little more. Not all at once, but piece by piece, planet by planet, light year by light year. And now, as we drift toward the end of this journey, let the weight of these discoveries settle softly around you. We've traveled far tonight, not in distance, but in imagination. From planets that rain glass to worlds wrapped in darkness, from hot Jupiters to frozen wanderers, from the closest stars to realms we'll never reach. Each one is real. Each one exists, somewhere out there turning silently in the vastness of space. You are lying here on a small blue world, wrapped in atmosphere and light. Above you, even if you can't see them, are stars. And around many of those stars, planets. Some are hostile, some are strange. A few, perhaps, are gentle. And on one of them, maybe, just maybe, something else is looking up at the sky, wondering if they're alone. But you're not thinking about that now. Your thoughts are growing softer, slower, like the orbits of distant worlds tracing their quiet paths through the dark. The facts have done their work. They've carried you here to this place of rest, where the universe feels both impossibly vast and somehow quietly close. There's nothing more you need to do tonight. No problems to solve, no questions to answer. The planets will keep turning, the stars will keep shining, and you, here in this moment, can simply let go. Breathe slowly. Let the images fade. Let the words drift away like clouds across an alien sky. The universe is vast, yes, but right now, it's also simple. It's just you here now, resting. If you're still awake, that's okay. There's no rush. The planets aren't going anywhere. They'll still be there tomorrow, and the day after that, and for billions of years to come. You can return to them anytime you like. But for now, let yourself rest. Let your body sink deeper into comfort. Let your mind release its hold on waking thoughts. And if these distant worlds, these strange and beautiful planets, have helped you find your way to sleep, then they've done exactly what they were meant to do. The universe is patient. It has waited billions of years, and it will wait a little longer. But you don't have to wait. You can rest now. Thank you for traveling with me tonight across the cosmos, from world to world. If you'd like more journeys like this, gentle explorations of the universe designed to help you rest, consider subscribing. There's always more to discover, one quiet fact at a time. But for now, sleep well. Dream of distant skies, if you dream at all. And know that somewhere, out there in the dark, a planet is turning, silent, alone, but not forgotten. Good night.